I think many of you are still joining. But anyway, let's begin by that time. Let me share the screen. So we are talking about the clustering algorithm, and we started with K-means clustering. So we are talking about K-means clustering algorithm. Sorry, I got disconnected in between. Can you hear me now? Am I audible? Can someone confirm? Okay. Yeah, so we are talking about k-means clustering. We said that it partitions the data points based on the distance between them, trying to group the data points with less distance together and put data points with high distance into separate clusters. We will also see the small example to understand how k-means clustering works. For example, if then what we do is in k-means clustering, what we do is we start with any two random cluster heads. So first thing we do is we decide so total number of clusters that we want to create is decided a priori or it is known in advance. So there is a particular characteristic of the algorithm which often becomes limitation because many times when we are working on real data, we do not know like how many groups or how many partitions we want to create from this data. But k-means clustering algorithm requires that we need to know the number of clusters in advance, and then we randomly select clusters from the data points. So, for example, as we discussed last time, we can choose 2 points, like let's say C1 and C2, as initial cluster heads. Which we have randomly selected. And then so once first we decide, then randomly select. We randomly select initial cluster head, and then we calculate distance of each data point from both clusters. So once the data points are distance of data point from the cluster head is calculated, we merge the data point or we assign the data points to the nearest cluster head. So the cluster head from where the distance is minimum, and then we create the initial clusters. So maybe initially in this example, the cluster might look something like this. Or maybe there might be some iterations of the algorithm also. For example, if you are taking decision for this data point, right, for this one. So if you notice its distance from C1 is less than the distance from C2, though I have not actually drawn anything to scale, but from visual inspection it looks like that. So in your first iteration, you might get something like this. So for this, I am saying that this distance is less than this distance, right? And for this case, second case, this one, I guess this distance is greater than this distance. So your initial cluster, in your first iteration, you might get cluster like this. So that will be first iteration. Randomly initialize cluster heads and assign data points to nearest cluster head. That is first step. Is this clear to everyone? Are you with me on this? Is this clear? Okay, so if this is clear, then we can go a bit more detail, do a bit more detailed analysis. So now once this is done, after first iteration, what we do is, so first step is calculate distance of every data point from all cluster head. Then calculate, or rather calculate centroids of newly formed clusters. That is, this centroid will become new cluster head. So this is where the technique derives its name, right? What we do is we take mean of these data points, we calculate all these vectors, we calculate mean, and we make a new centroid. If the data is something like this, then maybe centroid of C1 will be something like this. So this becomes So this becomes a new C1 now. And similarly, there will be here new C2. In iteration 2. And I hope you remember what we did to find out these new centroids. We take average of value of all data points assigned to that cluster. Right, so now C1 and C2 has shifted. C2 has shifted a bit leftwards. C1 has shifted a bit right. Sorry, C2 both has shifted a bit leftwards. And now from this new dots, which I have shown as blue dots, now if you calculate the distance of x1 from these new data points, again we repeat the process. Once the new cluster head are formed, we repeat the process. So if you see the distance of these data points from C1 is now more than distance from C2. That purple line that you can see on your screen. So when you repeat the process with new cluster head, the data point, as I marked with question, let's call it point P1. This P1 will now be assigned to cluster 2. And after second iteration, your clusters would look something like this. Right? So this is how the mean of data points is playing role in improving the cluster with every iteration. Are you with me so far? Please think of this for a while and ask me if you have any doubts. So is this clear to everyone how k-mean clustering is working? Okay, Dev has confirmed yes. Okay, good. Devansh also says yes. Okay, good. So where every time we calculate mean of the data points in the current cluster and make it a centroid so that the cluster head remains somewhere in the center of all the data points, and so that the distance from the some wrongly classified points would increase, and eventually it gets correctly classified. So it can be proved that with sufficient number of iterations, we will reach the let's finish these steps first. So calculate center of newly formed clusters. Centers are now new cluster head, and repeat process of assigning data points to cluster head and calculating new cluster head. Repeat this until the cluster becomes stable. What do I mean by stable cluster? Stable cluster means data points in all clusters are same as previous clusters. Right? This is what we mean by stable clusters. So as we have seen here, in first iteration, the data point P1 has moved from cluster 1 to cluster 2. So we need to iterate one more time and see that if there are any other points which are reaching cluster. We keep on repeating this until we reach to a level where there is no movement of data point from one cluster to another. And when we reach there, we say that the clusters are now stable and algorithm can stop. And how do we know that the algorithm has performed well? So how to measure? Quality of clusters. So there are two measures. One is intercluster distance, and second is intra-cluster distance. As the name suggests, you would know the difference between them. Inter-cluster distance means how closely the data points within the cluster are connected. And intra-cluster distance means that how far the clusters are from each other. So as from the name suggests, I would ask a simple question like, what do you think that, do you want high inter-cluster distance or high intra-cluster distance? What is your opinion? Intercluster distance should be high or low? Dave says that high intra-cluster distance. Yes, so clusters should be as far as possible from each other. For example, here in first iteration, if you see what we have done through two iteration, in first iteration, C1 and C2 were crossing each other's area. In second iteration, separation is better. So yes, high intra-cluster distance and low intercluster distance. We want data points to be together as far as possible. Yeah, so these are the way to measure the quality of clustering. The cluster that we have formed, if it has very high intra-cluster distance and very low intercluster, sorry, yes, very low intercluster distance, then we say that we did good clustering. Now let us see when we face problem with k-means clustering. So one possible problem with k-means clustering is when data points are where there are many outliers in your data set. By outlier, what I mean is if your data points are something like this. If your data points are something like this, and you are trying to do clustering, then what will happen is this outlier would shift your mean drastically. For example, if I had this cluster, and if I add this new data point into this cluster, the new cluster will become something like this. And it will shift mean from here to somewhere here. Right? So outliers will drag the value of mean towards them. And outliers are the data points where you don't see much of the data. So it is possible that the algorithm would suffer due to outlier. Plus, if unfortunately when you're randomly selecting the mean k means, if you end up selecting outliers, then all your calculations will be very bad. For example, if this is selected as cluster head, then you won't be able to do much, right? This will remain in the same. Then if you start with this cluster head and this cluster head, then your algorithm will do clustering like this. This will be the cluster 1 and this will be the cluster 2. And because nothing is near to C1, everything is near to C2, so you will get cluster head of C2 there. So K-means algorithm is prone to outlier and doesn't perform well with outlier. When there are outliers in the data. And second thing is number of cluster heads. Number of cluster heads are fixed and randomly assigned. These are the two main limitations of K-means clustering algorithm. Now we'll see that how to address them. But before that, I would like to bring your attention to something which we claimed in lecture of expectation maximization. We say that K means K means is a special case of expectation maximization. Do you see the similarity or differences between them? Do you want to make any comments here? Just think of it for a while and tell me. I think I got muted in between. So can you hear me now? Can someone confirm if the audio is coming through properly? Okay. So I was talking about uh, K-mean is a special case of expectation maximization. If you remember, we did this during our discussion of expectation maximization. And can you relate how it works, or are you able to relate between K-means and expectation maximization? Does anyone want to make? Okay, Prince is saying EM is finding likelihood of an observation belonging to a cluster. Okay. Yes, it sounds correct answer, but can you give more intuitive understanding of how K-mean and expectation maximization are similar, or how why K-mean is considered a special case of EM? So let's say these are the data points x1, x2, and h. H is our hidden variable for which we do not know the value. What we do in EM is we iterate between 2 points. One is estimate theta, and calculate h. Right? So there are two unknowns, theta and h, in case of expectation maximization. So we first start with random theta. Remember, we randomly initialize the probability values. Then based on those probability values, we calculate h. And then based on the new h value that we calculated, we re-estimate the probability. And we keep on iterating between these two until we reach a stable assignment, or we say that there is no further updation in the parameters. So there are two steps, expectation step and likelihood calculation step, as Prince is saying. Expectation of random variable h and calculation of parameter theta, which is likelihood. Right, Prince? Okay, so this was expectation maximization. Now let us see how it fits the idea of K-mean clustering. So this h, now h is cluster. So let us say we are dividing data points into two clusters, as we are doing in previous example. We are dividing data point into two clusters, C1 and C2. So this H can take value of C1, C2, C1, and so on. So how does the algorithm work? Now I will speak about expectation maximization. It will look like K-means. Randomly initialize cluster head. So randomly calculate parameters of C1 and C2. And when we know that in Bayesian network, when we talk about continuous variable, the parameters comes from a Gaussian distribution. So that becomes mu1 and mu2, sigma 1 and sigma 2. So randomly start with two cluster and estimate its mean value. So that becomes mu and sigma. So that becomes your new cluster head. So initial start with two assignments, C1, C2. That is your initial estimate of parameter. Based on your initial estimate of parameter, assign cluster to every data point, that is calculate H. So this is initial cluster head. Right? Then this is recompute centroid or mean, that is new cluster head. And this is assign data to cluster or assign cluster label to the data points. Right? So when you assume that it is Gaussian and you are working on mean, the expectation maximization algorithm essentially becomes kind of k-means clustering algorithm. And as this is expectation maximization algorithm also reach to a assignment where there is no further updation in parameter. Similarly, k-means also will reach to a stage where there is no updation in the no updation in the cluster, and all the data points are stable in the inside the cluster. This is where the algorithm ends. So this is how expectation and maximization is related to cluster. Now let's talk about these two things. So one is issue of outliers. We said that k-means algorithm suffers due to the issue of outlier, and for that a variation of k-means algorithm is proposed, which is known as k-middoid clustering. So as the name suggests, instead of finding mean, we calculate middoid here. And you know that median has a benefit that it is a data point, not the random mean value. In case of k-means, your mean may not be a data point after a few iterations. That's why the mean can be shifted by the outlier data. So if we go back to the same figure again, so instead of calculating mean, we look at actual data point, which are cluster heads, median finding, or some other technique through which we can declare a nearest candidate as the cluster head. So let's see how it works. Again, let's take the same example. We have selected this as C1 and this as C2. So in first iteration, you assign data point to nearest cluster, and after iteration 1, your cluster would be something like this. Last time our argument was that after first iteration, the mean would shift towards this side. Now what we do is, instead of calculating average of all data points and make a mean which is not the real data point but some number, what we do is we make a real data point mean. And how do we do this? So calculate distance. So where it differs, the algorithm differs at the point of updating cluster heads. So what we do is we recalculate cluster head from data points. So calculate calculate distance of a data point from all other data points of the cluster. So for example, now if when I want to update the mean, what I will do is I will calculate distance of all other points from this point. And the distance value for this data point will be sigma of all this distance is divided by the number of data points. In a simple words, it is average. So this I will do for every data point. For every data point inside the cluster, I will calculate this sigma di upon n, the average distance from all other points. Let's call it distance of average distance we are calculating average distance from all the points in the cluster. And after doing this, we will choose the one which has minimum distance. And choose the data point which has minimum average distance from all of the points as the new cluster head. So if you notice in this case, again the C1 will become the new cluster head. Or rather it will remain the cluster head. Because visually we can see that it has minimum average distance from the data point. It won't go towards this or this because it has average distance from all of the data point very high. Right? So data point remains C1 and so on. So this is how K midweight clustering works. And as we can see, it does not suffer from outlier, or it rather tries to address the issue of outlier that we face in K-means clustering. Otherwise, idea-wise, it is pretty similar to k-means. It can be counted as a variation of k-means only. But the problem is now this middle calculation is very cumbersome task. If you see, they're calculating average data points from all the data points every time. It is a very time-consuming task. And there are various ways of doing it also. There are many variations. And there are many approaches to do this also. But we will not go there in discussing that. But we'll keep the discussion of partition-based or distance calculation-based clustering method up to this. So I will stop here. And please ask me if you have any questions or any doubts on this. Is this clear? Any questions? Okay, so if there are no other questions, we'll end the meeting here. Thanks.